tab. Okay, so today we'll continue the rest of the lesson. So now we go to understanding charts. Okay, now the interesting thing is when we talk about like Elasticsearch, right? It is actually a wrapper on top of Lucene. So probably you've heard of this already. So the interesting thing is, what is the Lucene then? I mean, yeah, we're wrapped on top of it, but where is that Lucene? So in general, when we talk about something called index, right? The data index is built on top of something called shards. Okay, so that means one data index equals to n shards in general. All right, and so this shard thing is actually an instance of Lucene in general. All right. Yeah, so that's why we've been kind of like talking about Lucene for quite some time, because when we talk about the data index is built on top of something like multiple shards, primary shards, etc. But actually a shard is a Lucene itself, all right? So that's why I'm here, second big bullet point. Each shard is actually one instance of Lucene. It contains all the data in any of the documents. So that means what? That means if you pump in a JSON document, so this JSON document will be saved inside one of the shards. And because shard is actually just a Lucene, so that explains why we are a wrapper on top of this technology. And remember, each data shard should be allocated to a particular data node as well. All right. So that's the reason why we said when we want to scale up the architecture, we need more data nodes, because more data nodes, each of them can share some of the loadings of one particular data shard in general. So in the past, right, in the earlier versions of Elastic, each data index is comprised of 5 primary shards in general. So that's why I can see in this chart here, if we have something called my index, it will be written like this way. It'll be kind of like composed by 5 primary shards. And some of the primary shards will go to node 1, for example, and the rest will go to node 2 in this case, right? And so you can see the optimal number of the data nodes in this case should be exactly 5 data nodes, because now exactly one data node will have one shard to serve in general. All right, so that's the simple answer in here. But of course, in real life scenarios, we have so many data shards, right? Probably we won't be having too much data nodes unless you have enough budget or licenses, right? So that's why having like a 5-node cluster and each of the data nodes contains like more than tens of shards is actually okay. All right. But anyway, if you have enough money, you can actually expand the architecture to like some 20s or even 100 nodes, not shards. All right. It's actually possible. Just a matter of money. So then another important concept is something called primary versus the replica shards. So instead of like going through the slides, I'll actually go to a drawing board. Okay, so now let's take an example. If I have only one single data node, okay, so this node 1. If we create just a normal data index with 3 primary shards, because there's only one node here, right? So all the primary shards will be allocated to this one and only one data node only. So for example, node 1 will have shard, damn. Please wait. So we'll only have all the data shards be allocated inside this node 1, because this is the only data node to contain all the data. So in general, this doesn't scale, right? Because it's a single point failure. So then usually when we have some budgets, we will introduce more data nodes. For example, node 2. Now, once node 2 comes into action, we will start to redistribute the shards. Now, take example, maybe shard 1 will be moved over to this node 2, all right? So this is how we do scaling. So theoretically, the optimal number of data nodes for this example should be exactly 3 nodes, okay? The reason is if node 3 was introduced, one of the data shards will actually go to this node 3 now, right? So this is how we scale up, all right? So the more data nodes, as long as enough data shards, we can actually scale the operations, because this machine, for example, can take up 1,000 ingestion per second. This one probably also 1,000. This one also 1,000. So we increase the maximum of ingestion to 3,000 per second now instead of only 1,000. All right, so that's how we scale up in general. But then let's go back to the story, right? Don't make it too complicated. So let's just make sure that we only got 2 nodes now. Okay, so I'm removing this node 3. All right, so we only got like 2 data nodes, and then because of this, we redistribute the shards in this common way. All right. Now, this is actually not the final solution for a normal architecture, because you can see if any of the nodes are actually offline, you still will have partial data only. Now, take example. If this one is offline, all right, now you only got node 1. And node 1 only contains shard 0 and shard 2. So shard 1's data are not there. So that means this is not a very good optimal solution. And that is the reason why we introduce something called replica shards. Okay, so assume that this machine is still here, okay? These 2 machines are still here. Now, what we're going to do is to create a replica. A replica is actually a copy of the same data. So in general, it will also consist of shard 0, shard 1, and shard 2, all right? And so here, we will rebuild the missing shard 1, the missing shard 0, shard 2. So we call this the R, okay, the R1. And the blue ones are actually the primaries, okay? Now, this is actually a better solution, because if this side is offline, all right, it's still good, because inside the remaining node 1, we still have shard 0, shard 1, shard 2. So that means the full set of data is still here. So we didn't really miss any data documents, all right? The only thing we kind of like miss is the 50% of the processing power, because node 2 is offline, all right? So that's why this is a much better solution, right? And so let's continue the story, because this is not the final step. Now you might start to ask is like, if I got replica shards out, the green ones, as well as the blue ones, the primary shards, what are the differences? The differences is whenever we want to do updates on the existing documents, we actually need to go to the primary shards first. So primary shards is kind of like the original source of truth. So if you want to do something on the existing documents, find the primary shards first. Let them update. And then the corresponding update will be passed on to the corresponding replica shards. So that means in my current situation, I've got primary 0, primary 2, but not primary 1. So that means if there's any data that needs to be updated on the shard 1, it will fail, because we do not have a primary shard 1. So that's why final step for this architecture is I would need to do a promotion. So this shard will now becomes primary shard 1, promoted. Okay. Now remember, the idea is because only primary shards can update the existing data. So if I do not have this primary shard 1, this shard 1 will be read only. So it cannot really kind of like operate like a normal data index anymore, because some of the data parts can not be updated. So that's the reason why we need to do a promotion. And so now this so-called replica 1 becomes the primary 1, all right? Now the final piece, of course, is when this thing is coming back into action. So maybe after some time, node 2 comes back, all right? All right. So what really happens is because now you already have all the primary shots on node 1. So the remaining shots that's missing is only the replicas. And so that is the reason why here you will have all the missing replicas now. All right. So that's the point. So remember, when you have a new node joined, or maybe the so-called damaged node returns to the cluster, it will check with the existing master node to see what is missing. So take example in here, we're just missing the replicas. So just recreate the missing replicas on node 2, and that's it. So that's the full story in general. So after understanding all these things in graph, these slides can kind of like skim through because we already gone through all the concepts. Now, some of the pieces I will need to re-emphasize though. Remember, there are two basic types of shots inside your Elasticsearch cluster. The first one is the set of primary shots, which is the original shots, or I would say the original source of truth. Now, remember, every single change on existing data, including pumping new data into a particular shot, we need to have the primary shots there because they are the ones that accept the initial write operation. And then it will sync back to the corresponding replica shots. So that's why primary shots are very important. In general, whenever you create an index, you will be creating primary shots. All right. Then, if you have any capabilities, create the replica shots. So on the other hand, replica shots are just a copy of the primary shot data. Okay, the shots of block data set, right? By default, if you're using Elasticsearch version 7 or some other older future versions like version 8, we will default the number of primary shots to 1 though. And we'll actually talk about this a little bit at the very end of this lesson, why we actually shrink from 5 primary shots back to 1. All right, so there's a reason, because there's some performance issue if you do not care too much about it, all right? Now, the important things on this slide is talking about the relationship between primary and replica. So basically, a primary and its replica cannot be on the same node. Telling me what? So that means if you have a primary shot 0, you cannot have a replica shot 0 on the same node as well. The major reason is because if we let you do so, that is also another single point failure. All right, if you go back to this slide, right? Okay, just clear this thing a little bit. Okay, node 1, node 2. If we have a primary shot 0, and then a primary shot 1, and then 2 here, and then we let you create a replica shot 0, and then replica 1, and 2, what really happens is if this side is offline, all right, on this side, you only got shot 2, shot 1, shot 2, but where's the shot 0, all right? Damn, I really don't like this thing. Okay, so where's the shot 0? So it's not there. So that's why we do not let you do this kind of operation. Because if you have the same primary shot and replica shot on the same machine, there's a big chance that if this machine is offline, the remaining nodes inside the cluster will not have that piece of that shot data. Okay, so it's kind of like a single point failure again. So that's the reason why the same primary shot should not have the replica shot with the same number on that particular data node as well. All right, instead, it should be on another data node. So it's kind of like HA. You cannot have everything in the same basket, all right? So how do we configure the number of primary shots then? Now, the important point is for primary shots, you can only set the number of primary shots for once, okay? So I'll write it down here, primary shots. Set for once only, okay? That also means that once you created the data index, you cannot change number of primary shots. So it's forever. It's a forever setting. All right. So the only way to set it is through the creation of the data index only at that time. Now, take example, we put my new index and settings number of shots to 3. So that's the only way to control how many data shots you have for this index. And that's it. And if you find that, hey, I want 5 primary shots instead, sorry, you can't do that. You can't change it anymore. So the next time when you create a related index like my new index 2, you can set it to number of primary shots 5, but not the original one, because you can only set number of primary shots for once. Okay. So here you can see the last bullet point. This value cannot be changed. Done. Okay. So think carefully when you create the index. Now the discussion, why we drop from 5 primary shots back to 1 primary shot then? So in general, the simple answer is every shot is a leucine, all right? So leucine is itself a Java program, or maybe a Java library, you can say. So that means when we have an index with 5 shots, we're maintaining 5 instances of leucines in the memory level, all right? Even though this leucine might not have much work because you didn't pump in much data to it, but still it maintains a minimum limit of the resources. For example, the number of file descriptors, the heap, and also probably some file IO operations to do some housekeeping things. So that's why even though you have no special task on this particular data shot, you still use up some memory and resources. And so that's why if you think of the time-based indices, that is every day you create a new index, every day you're going to create 5 shots. Okay, no matter what is the workload, you have 5 shots in memory, increase that per day. So after like a month is 30 days, right? Times 5. That means at the end of the month, you already have 150 shots inside your memory level. So that's only 1 month. What about 1 year? Times 12. So times 12 probably is already like nearly how many? I think it's 1,700 something, right? So you have like 1,000 something shots per year. And usually our architecture will run for some years, right? Maybe 5 years times 5. So that's pretty much like over 9,000 shots then. So to be honest, even though you have the most powerful machine inside your architecture, is it possible to hold up 9,000 leucines at the same time without any issues? I really doubt, right? So that's the reason why we reduce the number of primary shots back to 1, all right? And if you do so, now after 5 years, you'll find that you only have 1/5 of these 9,000 something shots. So probably you just get back to 1,700 something shots after 5 years, all right? So your hardware can sustain much longer instead of like holding 9,000 shots. So that's one of the major reasons. And the second reason is because each of the data shots, they can actually hold up to at least tens of gigabytes of data. So here, there's a line, I think it's the third line, at least tens of gigabytes of data, right? So that also tells us that if your data set is very small, because we start from small usually, but after a few years, it might grow. So there is no point to have many data shots for 1 index per day if you don't even have like 1 gig of data. I mean per day level. So there's no point to have like multiple shots. 1 shot is very enough. So that's why we go back into something like a 1 shot policy. All right. So some more details will be discussed in Engineering 2 about the sizing, that kind of thing. But the short answer is, remember, your data shots, you should have at least a volume of like some tens of gigabytes of data. Then you are kind of like optimizing the environment and the settings, all right? If not, you will find that you've got only some 100 megabytes of data per data shot. Probably you should reduce it back to 1 primary shot for that index instead, right? And the details like how to do so is actually available in Engineering 2 when we run something called reindex or the shrink API, or sorry, not shrink. Shrink API in this case. Shrink API instead. all right? Just to let you know, all right? So if you really need to do this kind of exercise, you can actually go to the official documents and search for the key terms called reindex or shrink APIs. Or maybe join the course later on. Now, what about, on the other hand, the number of replicas? Now, replicas is talking about the number of copies of the same data. So remember, the major reasons why we have this copy is we want to have resilience, all right? If something happens on one of the data nodes, we assume that the remaining node still has a complete set of the data somewhere, all right? Or maybe from different shots, they can still combine to form a full set of data. So that is the idea about why we have replication, right? So by default, if we didn't set anything, the number of replicas is always set to one, okay? So we just need one copy of the data somewhere in the cluster. So again, if you want to kind of like set this value, you can actually set it through the creation time of that index by setting number of replicas. Now, for example, I set it to 2 here. That means I should have 2 copies. Okay, so you will see 2 R0 inside the cluster. All right. So now, important things is number of replicas can be changed at any time. So the last point, number of replicas can be changed at any time. So this is a big contrast comparing with the primary shots, right? So replicas can be changed freely at any time. Remember, the important concept is primary shots. Once you set, they are always there. You cannot change it to another number. But number of replicas, they are always changeable. The reason is because we want flexibility. Sometimes we might want to have a set of copies, all right? But sometimes we don't. So we're talking about the don't scenarios is when we have a lot of data to pump in, and we do not want to waste time to update the replicas at that moment. So we can actually change number of replicas to 0 if you want to. But later on, we find that if we want to kind of like scale up the search function efficiency and so on, we might want to duplicate more of the same set of data inside a cluster, so that at the same time, more search requests can be done as well. So that is when we want to increase number of replicas. So that's the reason why number of replicas is kind of like flexible in changing the number sets, right? But not for primary shots. Some other reasons why we have the replicas is, of course, HA, high availability, so that we still have the same data set somewhere when a node is gone. The next one is because like what we just thought about, kind of like discussed, is the search throughput, because we want to make sure that more data are available inside a cluster to serve the same search request, all right? Some other things about the cluster itself and the shot related things is the shot allocation. So this thing, we'll actually go through that again in the last big module. So now I just kind of like skim through it. So there is actually a API called cat cluster health, which we can check the health of the cluster in general. And this API returns some information about how many primary shots you have, as well as how many total shots you should be having as well. All right, so it's kind of like a very simple API to let you know the general health of the cluster. So in general, cluster health contains 3 colors in general. You can see that it's either red, green, or yellow. Now, red is actually very bad because you have one of the data shots, the primary data shots missing. So you're missing data. So that's why it's a red. Now, yellow means that all the primary shots are here, but the corresponding replica shots is not complete. Okay, so maybe you do not have enough data nodes to store the replicas. Okay, so in general, so it means that it's not the end of the world because all the primary shots are here. Just the replication is not complete at this moment. Now, finally, green is the most perfect situation in which all the primaries and replicas are there. All right, the best, perfect state. Shot allocation. So in general, each shot will go through some life cycle stages in general. All right, take example, we will be going into the 4 states now, like the unassigned one, initializing, started, relocating, etc. Now, the important thing is all these state changes are handled by Elastic automatically. So there is no human intervention. You do not need to run APIs, right? Now, let's start with the unassigned state. When you just created a index, right, they are usually unassigned yet because you do not pump in any data. So it's kind of like a little bit inefficient if you create empty lucines, right? So that's why we do not create these shards until you pump in the first document, right? So that is what we call unassigned stage. Later on, when we have some data coming in, we will start to initialize and create the real instances of those shards. Now remember, primary shards are always created first because they are the data owners. All right. If you want to make changes, you always go to primaries first. So that's why primary shards must be created first. So that's the initializing stage. After some time, assume that now the primary shards are ready. So they will change into something called started status. Right. And so it's ready to serve. So you can start pumping data in, do search, etc. And then the corresponding replica shard will also start to initialize, right? Create a missing piece and start singing data between the primaries and the replicas, etc. So eventually we'll go into a so-called status quo in which all the primaries and replicas are there, also started. So that is the green color status. Now, scenario 2 is after a while, we have some budgets, we add some new nodes. So what really happens is we redistribute the shards because if we have new nodes, right, we should make use of them to work for us, just like normal human companies. If we said that we are overloaded with work, we try to hire people. And once we got the new hires, we shift some work to them. All right. If not, why should we hire them? Let them sit here and get salary? No. All right. Probably they need to do something. So that's the same thing. When you introduce new nodes, we start resharing the shards. And so this resharing is totally controlled by the master nodes. So they will know, or maybe not know, it's just say they decide which nodes should actually share this data shard. And so we will start to do relocation. So now you can see now the P0 on node 1 is relocating to the node 4. And so on the node 4, the P0 will be in initializing stage, singing or copy the data from node 1. All right. Now, after finish relocating, you will see that the original shards should be removed because now they have been, they kind of like logically relocated to node 4, for example. So there's no point to keep this P0 on node 1. So let's just physically delete it. All right. And now that means now node 1 has more resources to hold other data shards. And in the meantime, node 4 actually joins the cluster and serve as one of the members. All right. We redistribute the loading. Another scenario might be something like this. You might have a node that is offline. So maybe for maintenance or maybe it just crashed. Now, remember, the story is if you have one node missing, that means some of the shards are missing as well. So let's take a look on the remaining architecture. We've got P0, but there is no P1. We told you that we need to have primary shards available. If not, this index is kind of like not fully functioning. So that's why the first step is to promote the R1 to P1. Second step, there should be some other shards missing. For example, the replica shard 1 is missing now. So let master node find somebody to rebuild this missing R1. So maybe this time the lucky one was node 3. So node 3 now will be creating the R1 shard there. And so it goes back into the green color. So this is how we sustain, all right? So even though you miss some nodes or maybe sometimes you add some nodes, we will redistribute shards or build missing shards to make sure that the architecture goes back into the status quo. That is maybe green status, all right? So this is how we work. So in general, all these things are automatically done. So no API involved. All right, so we've told you that replications can be changed, right? Number of replica shots can be changed, but how to do so? So in general, it's just one single command like this. So we put the index settings and number of replicas to, like, for example, 3. Then we'll start to rebuild the missing replica pieces. All right. So here, there's a question. What's the cluster health? The cluster health here is yellow. The reason is because you need 4 replicas, 3 replicas. That means you need to have 1 primary shot. Okay, we've got P1 here, and 3 more replicas. So throughout the number of nodes, we can only create 2 R0. So 1 R0 is missing. So this is the case where we got a yellow. The replica set is incomplete, but primary shots are here. All right. So usually in production, you will be either in yellow or in green status. Depends on if you have enough data nodes or not. All right. But actually, remember, yellow is okay. It's still not the end of the world. But if you have a red, that is not good because the primary shots are missing. Summaries. All right. Now, the first point, Elasticsearch will subdivide your data inside the index into multiple pieces called shots. All right. And shots are actually Lucines. Okay. Hmm. Okay. The summary is not very important because they didn't mention the most important parts, I would say. All right. All right. The quiz. If number of shots is primary shots is that is primary shots 4. Replica set is 2. How many total shots will you have? The answer is 12. All right. Because you will need to have 4 primaries. All right. And 4 replica sets plus another 4 replica set. So you're actually having totally 12 total shots. Okay, so that is the point here. So don't kind of like mix up it's like 4 times 2 because it's totally not a thing. And having a wrong calculation on this might have a problem on your budgeting later on as well because you might need more nodes than you expected. All right, number 2, true or false. The nodes where shards are located are decided by coordinating node. No, it's actually master node. Coordinating node is just coordinating how the nodes work for us, but they do not kind of like decide where your data should be stored, etc. So it's actually controlled by the corresponding master nodes instead. Okay, our cluster of yellow status missing documents? No, it's missing a complete set of replicas instead. If we're talking about missing documents, it should be red color because you're really missing data, right? Now let's take like 15 minutes lap and or maybe rest. So now it's 03:15. Okay, so let's just come back around 20. All right, XX20. And then we'll continue the last lesson for this one. A little bit difficult to understand is distributed operations. For example, when you write data, how do the shots interact with it? And also when we search data, how do we interact with those shots that is having some contents related and some maybe not related, blah, blah, blah. So we're talking about the operations on write and read. Okay, now let's continue. We'll be talking about the distributed operations now. Now, the first thing is because we are a multi-node distributed architecture, plus we have multi-shots as well. Now, let's take a look on how do we actually write data to this kind of architecture. Now, for example, I'm going to do a put and put a document to document ID 551 like this. What really happens is we will need to go through a calculation, right? So this calculation is what I call the short hashing. So you can see the formula is kind of like running a hash based on the routing key and then a modulo based on number of primary shots. So in general, if we do have like number of primary shots of 5, right, we actually should get back a modulo resulting from 0 to 4. And this is a very important thing as well, because this number dictates where this document should be stored on which data shot in general. Now remember, we start with the zero-based counting. So shot 1 was actually known as shot 0 instead. And then we have shot 1, 2, 3, and 4. And that makes up 5 primary shots. So that's why this number is actually dictating where this document should be stored. If it results a number of 1, that means this data, this document should be stored under shot 1. All right, so that is how we do the routing and distribute your data in general. So now, like you said, if we put this routing key, so by default, routing key is your document ID, all right? If 551 after the hashing, modulo by 5, actually returns number 3, that means now this data should be routed to shot 3 instead. So the next step is, once we know that shot 3 is the one who's going to keep this data, we need to find out which data node contains this shot 3. So somehow it's kind of interesting that shot 3 was actually on node 3 as well. So we forward this request to that particular node 3 and let it do the ingestion. So after the ingestion has been done and no errors assumed, it will start to find whether there are replica shots inside the cluster. So if there was a R3 somewhere, we will actually forward this update to that particular node as well. In this case, node 1 has a replica shot 3, so it will need to accept the update. And so after the updates of R3, it will comes back to the original primary shot 3 and tells it that, hey, I've just got updated without any issues, blah, blah, blah. So the final step is, of course, this shot 3 will need to tell the original coordinating node, that is node 2, that everything's fine. We've succeeded in writing the data in the primary shot as well as the replica shot, etc. And so we can compile the final result and send it back to the client. So it's actually quite simple, all right? So you can see when we kind of like have distributed systems, when you write your data, the first thing is we need to know where it should be written to. That is to find out where is the primary shot. So that's step 1. And then step 2, primary shot needs to do the updates. And step 3, if there were any replica shots available inside the cluster, do the same update as well. And then later on, when every primary and replicas are updated successfully, return the final result. All right. So if one of the replica shots failed, it will just return you some error messages. And so it will send back to the client as well. So it won't kind of like roll back that kind of operation. Instead, it will tell you that the replica shots failed, all right, but the primary shots are okay, right? So that's the kind of operations that will appear. So what about updates and deletes then? So in general, updates and deletes is a little bit slightly different than writes, but still it contains overwriting something. So let's take a look on the simplest operation called delete. Now delete is quite simple because we simply just go to the corresponding primary shot and mark delete. Okay, so remember, we don't do physical deletes yet. We just mark delete and telling Elasticsearch that this particular document is outdated and we should omit them from being involved in the processing, etc. Right? So that is mark delete. So once we do the mark delete, that's it, right? So next time when we do a search, this particular document set will be ignored, all right? So that's delete. So then you might ask, when do we actually physically delete this operation or this document? We actually have something called a segment merge operation. So in segment merge operation, we do actually gathered all the related active documents together to form the final data structure and ignore the ones that has been obsolete. For example, the mark delete ones, we just gather them and just delete them through that process. All right, only when we do segment merge. All right, segment merge. Select. So that's the idea. So then what about updates? Updates is a little bit interesting because when we talk about updates, we're talking about something like you need to go back to the original shots to find out which document you want to do the update. All right. And then we mark delete as usual, something similar to delete. And then we do the updates in the memory level. All right. So for example, you want to change only the postal address. Okay, fine. I'll do that operation for you, but only in memory level. Then after every kind of change has been kind of like finalized, we will overwrite the same document again. So actually update means delete plus re-index a document at the same document ID. All right. So if you still remember, you've learned something called put, right? Put operation, you need to provide a document ID. So here we're doing exactly the same thing. So you mark delete the original one, and then you put the finalized content, the merged updates to the same document ID. And because by default, we simply just override it. All right. So that's why updates are actually just delete plus overwriting. All right. So that is also a reason why we told you that Elasticsearch is best performant if the data is write once and nearly never update. The reason is if you ever update these documents so frequently, we are always doing a delete and re-index operation. So this is going to hurt a little bit on performance eventually, especially when you have very huge number of writes all the time. All right. So that will be the point. So refresh interval. Now, another interesting thing about writing data to the distributed systems is we do not make file IO commits per document level. Instead, we will have a buffer. So this is what we call the index buffer in general. So the index buffer is roughly 10% of the heap that you provided for your JVM. So for example, a 2 GB JVM will probably have like roughly 200 megabytes of this index buffer. Now, this index buffer is important because when you index document, we push them into this buffer first. All right. So we will not do a file IO commit until either two criteria. Default one, every 1 single second, we'll look at the buffer. If there's something, flush it out and write to disk. So that's point one. Point two, if you have this buffer 100% full, or maybe 90-ish percent full, we will also flush it out to do a write. So these are the two criteria, all right? So that's the reason why this buffer is important, because we can buffer up something instead of like per document write to the disk. So when we buffer a few chunks, then we write it, of course, it will be much more efficient. The less file we involve, the better is the performance in general. So in version 7, we actually add some new mechanisms, all right? For example, if you never search data, you just pump in data, for example, logging use cases, right? And you seldom search them. In this situation, we will actually make the refresh period to be extended to unlimited instead of per 1 second interval, all right? So you can see in this chart here, if you have if you keep on pumping data, right? So now the shot is kind of like search idle. So you do not search it. So it will not refresh until you actually run a search later on, or maybe when this buffer is full. All right. And however, if you actually suddenly make a search, like maybe, I don't know, so you pump in data for some time, like 2 hours, suddenly do a search, it will try to make a flush at once. And then we will try to refresh everything and make all the documents searchable. All the files are committed, blah, 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 and then keep on running. And so now we redirect that research period to 1 second again instead of infinity. All right. However, after this search has been run for like after 30 seconds and no more search coming in anymore, we will actually tune it back into infinity for the refresh period. So that unless this buffer is full, we will do a flush. All right. So it's kind of like auto toggling the refresh intervals, either 1 second or infinity. So this is actually useful for many use cases, because for most of our clients, when they're using Elasticsearch, they just kind of like pump in data and kind of like never search them, or maybe they search it like only once per month because of report generation and so on. So that's why we can actually optimize these write operations a little bit by toggling this refresh interval. All right. But is it a really good thing? To be honest, depends on your use case, because if people are kind of like having regular search and regular index, actually this toggling is kind of like meaningless to them. How many recommendations shot for one index with 3 nodes in a cluster? Shot for one index? What do you mean by recommendation on what? You have a shot with one index, yes. And what are you expecting? For example, you're expecting the refresh interval here, or you are talking about number of shots or something. Number of shots. 3 node cluster. So you can actually, now this is again a logical question. So the first thing is I will need to know the volume of your data. Okay, so like volume of data per day. So if the volume of data per day is over like 10 gigabytes, all right, then you should actually set it to, in this case, maybe 2 or 3 primary shots. Okay, so that will be good enough. But if you say that per day you have less than 1 gigabytes, okay, then actually 1 is very enough. Even though you have only a 3 node cluster, 1 is enough. 8 gigs per 5 minutes. So 1 hour 60, 1 hour 60 minutes, that's 12, that is 96 gigs. Okay, 96 GB per hour. That is how many times 12? I need the calculator. 12 times 96, 1152, that's 1 terabyte. GB per day. So if we said that you can have 50 gigs, let's do a calculation. 23 shots. You should need like roughly 20 to 23 shots based on the calculation. And because you've got a 3 node cluster, so every node will probably have 7 shots. 7 something, 7, 3, 7 or 8 shots per node, something like that. Okay, so this is just a rough calculation, right? So probably you need like 20 something shots for this kind of loading, all right? So that you can kind of like optimize it. And because you only got 3 nodes, right? So typically how many number of shots might not be so important to you now, but later on, if you will expand it to like, for example, from 3 shots to, I mean, sorry, 3 nodes to like 5 or 8 nodes, then you will see the difference in the loadings. They will spread, right? For now, because you only got 3 machines. So even though you have like 20 something shots, it might still not seem to be very efficient, all right? But at least it's better than 1 or 2 shots, that kind of thing. Formula to calculate, there's no formula. Okay, so remember, if you read the slides just now, we told you that 1 single shot should be holding one shot should be holding at least tens of gigabytes of data. Okay. So for me just now, I'm just using like 50 GB per shot. Okay, as the unit. So that's why when you have like some thousands of shots divided by 20, by 50, we actually got the number like 23. All right, so it's kind of like estimations. Okay. And if you want to make it bigger, you can have like 100 gigabytes. Then it would just kind of like round down to like less than 15 shots. All right. So again, it's an estimation in general. So there's no formula. All right. So it's not like the Microsoft things. You give me an Excel and then we can calculate something for you. So that's actually cheating. All right. So there's no such thing in Elasticsearch because big data contains a lot of factors that affect the performance. All right. So that's why it's not like A plus B must be C. So we don't have a direct formula about that. All right. So even though we do have something like a formula in the cloud environment, but well, that's because we manage the cloud engines for you, the machines for you. So that's why we kind of like have a so-called calculation because we can control, like, for example, the hardware specifications. And so that's why we can control a little bit. But because you're now running by yourself, so probably we have no idea what hardware specs you're using as well. So that's nearly impossible to calculate. All right. So that's why we just calculate on the volumes and the shot so-called limitations so that we can get back this number, right? Yeah, so I can say is like if you can just try to introduce a bit more data nodes, it will help you a lot because you have so many. You've got like a terabyte of data coming in every day, so probably you need more data nodes. All right, so now you've only got 3. I suppose you should try to think about like having 5 or 8 eventually so that you can spread out the loading. All right, so now it's 3. If you increase it to 5, you kind of like increase the throughput by nearly 100%, nearly. All right, because it's kind of like double. So if you go to 8, you probably will have 250 something percent overall increase in your performance. All right, because you will be introducing like 1.5 times more processing power. All right, so you can check these things if you have those resources. Right. Okay, refresh parameter. So just now we're talking about something called refresh interval. All right, so that means if you didn't do anything, either you wait for 1 second to get the data right into this level and make it searchable, or you wait till that whole buffer is exploded, and so we're doing a flush at once. So either way, all right. However, sometimes we might want to make sure this refresh is done automatically and at once. So if that's the case, we can change the parameter to false, true, or wait for. So by default, it's a false, which means that it will wait for roughly 1 second. All right. And if you set it to true, it will actually force this write operation to flush at once. All right. And the last point is wait for. Wait for is kind of like similar to false, which means I will try to call Elasticsearch to do the update. But at the same time, it's kind of like we wait for the document to be updated, then we search it and return that prompts to you. So it's kind of like synchronous operation. We wait till the operation has been done, then we come back. All right. So I guess the only use case why we need to have a wait for is because we are running something like a workflow. So you need to make sure that the corresponding document is searchable before you continue to step 2, that kind of situation. All right. So that's why for most cases, come on, just skip. All right. Just use the default skip because like waiting for 1 second for humans is actually not something very long unless you're running something like a process, a workflow inside a program. Then 1 second can be a very long time to a program. All right. But to humans, come on, 1 second is just done. All right. So it's actually not something really that long, to be honest. So wait for it is actually okay. So then we were talking about just writing data into the Elasticsearch clusters, right? What about searching these data then? Actually, search is much more complicated than write. Because right, we just need to know where we should push that document to, and then to update the replicas, and then done. But search, actually much more things we need to do. Now search is pretty much like this, right? Remember, because now we've divided all your data into different shards. Okay, so remember, each document has a routing key, so it will be routed to shard 1 or shard 2 or shard 0. So that means all your data are scattered around the data shards of this index. So then if you want to do a search, we need to go to every single shard and look for the results as well. Because we never know if there's a result inside shard 0 or shard 1 or shard 2. So all the shards, we need to go into them, make a search. All right. So that is the idea about search in general, right? So let's take a look on this scenario. So usually when we talk about search, we will divide it into two phases, query and fetch phase. The first phase called query is talking about finding a match in general. Now, the first thing is when we get this request, for example, node 1 is the one that get the request, it becomes the coordinating node, right? We've learned about this already in yesterday. So this coordinating node would now need to know which data nodes contains the shards to fulfill a search. Now, take example. We know that now on node 1, we have some shards called primary shard 4, and then we have replica shard 0 and 1 in node 2, and also the replica shard 2 and primary shard 3 in node 3 to help us to create the search results. All right. So then this is one of the things that you need to coordinate during this query phase. All right. You can also see that the interesting part is we're not taking all the primary shards into account. We're not taking P0 to P4 to run this search. Instead, some of them are P, some of them are Rs, replicas. So this thing again is controlled by the coordinating node at this moment of time. So it will pick the correct or suitable shards to help us, all right? But the important point is it must consist of shard 0 to shard 4, okay? That is the 5 shards. But we do not need them to be all primaries or all replicas. We just need them to be a mixture, all right? The reason is because we are distributing the loading again. You can see here, node 1 has 1 shard running, node 2 and node 3 has 2 shards running for us. So we distribute the loading again, all right? And so now we go into every of the corresponding shards and start to look for a result for your query. And so every shard will pick the top 10 results to us. So remember, it's every shard. Okay, so every shard will pick the top 10 hits and return the corresponding metadata to the coordinating node, that is node 1. Now here, the important thing is I say metadata. So I'm not returning the actual source of that data. Instead, I'm just returning the minimal information, like for example, what? Document ID, sorting values. That is, in general, score. All right, I'm only returning these minimal data to the coordinating node. And then the coordinating node will do a final sorting based on this sorting value. Now, you might guess why we do this kind of resorting. The reason is because every shard has its own top 10 results, of course, right? So it's just like in a university or maybe in a normal primary school. We have like maybe 6 primary 1 classes, right? Like 1A, 1B, 1C to 1F. And so every class should have their top 10 students, right? And so now we pick those top 10 students out from each of the classes and compete again based on their final exam results. And so we can resort these numbers, these students' exam performance again, and we found that, okay, so now this is the final top 10. So some, maybe 2 of them came from 1A class, and 5 of them came from 1C class, and some others came from 1F class, etc. So these are the real top 10s within the whole primary 1 section. So this is the idea. So even though each of the shards have their top 10, we need to do a final sorting to make sure that we are really taking the real top 10s within the whole data set. All right. And so that is the reason why we only return you metadata. All right. We just return you the minimal data required to do this final sorting. And once we get the final top 10, we will go into the fetch phase. The fetch phase is where we actually go back into the real shots to grab back the original source of data. So when we're talking about original source is exactly this one, the source field. Because source field is the documents that you come in at day one. All right. So that is the actual data that you really supply to us at the very beginning. And we return that one to you again. So the other reason why we actually just throw you the metadata at the very beginning during the query phase is if we return all the source by default. All right. So if we have, like in this case, 5 shots, right? Times 10 hits per shot, we actually yield 50 records or documents. So out of the 50 documents, we only need top 10. So 40 documents are actually wasted. So there's no point to return the big original source for all these 50 documents at the very beginning, because you're going to waste 40 of them. And all these things require a network bandwidth. All right. So that's the reason why, for the first time, we just grab back the minimal data, scores, and the .IDs. And the next stage, when we really fetch the final documents, we will go to grab back the real source, which might be over some 1 or 2 Ks of content. All right. That is actually for optimization purposes. All right. So that's why I say our search is much more complicated than ingestion, because simply it's a 2-step process. All right. For index, it's usually just 1 step. Pump it in, and they will automatically handle everything for us. But for search, we need to at least know where to grab the data, and then we grab back the metadata for comparison. Then we really fetch the finals. So it's kind of like at least 3 steps. All right. So this is a very good lesson for you to understand the mechanisms behind Elasticsearch in general. When we redistribute, because we're a distributed system, you need to know exactly what kind of operations should be done for writing data and searching data. And so this is actually a fundamental understanding, because later on, when we talk about why sometimes we're not 100% accurate, it's also because of this distributed behavior. Because we distribute the data in different shots, there might be a chance that some of the shots have a lot of similar data sets, all right, similar values. And so when we pick the samples out, like the top 10 results, we might miss the others as well. So that's why there might be inaccuracy issues. But we'll actually discuss about this kind of thing when we go into engineering 2. So for now, just understood that there might be that kind of situation. And all is because of distributed computing, right? So that's why it's not perfect, but for most cases it's okay, because it's big data. Missing a few samples will not really affect the final result. So actually, kind of like we say, is like if you are actually studying machine learning, all right, you actually will also face the similar scenario. Or AI, you also will face similar things, because it's full of big, huge data sets. And probably we'll be missing out a lot of them because we're doing sampling for most of the algorithms. All right. But eventually these results, the results evaluate are still acceptable. So that's why for Elasticsearch, it's the same thing. So we'll be kind of like sacrificing some of the samples to get efficiency instead of like waiting forever to calculate something very simple. All right. So if you use Hadoop, you can take every single document to do the count, but it will be super slow. So that's why it depends on what you're looking for. It's like efficiency or actually 100% accuracy, right? So for some of the questions, right? Number 1, index operations has to be executed on primary shards before being synced to replicas. This is true, because primary shards are the original source of truth. Number two, after index operations, documents might not be searched for up to 1 second. That is also true because we have the index buffer buffering these documents, and every 1 second we'll flush them out for write operations. After the write operations done, then you can search them because the data structures are finally created. Right? The doc values, the inverted index, they are finally created when you flush them. All right. So that is why you might need to wait for 1 second. All right. Okay, so the last one is talking about wait for, right? So wait for means that we will try to write a document to Elasticsearch and tries to wait till this document is searchable and then returns the prompt to you. All right, so it benefits when you want to make sure that a particular document is indexed and reachable before you continue to step 2. It's kind of like a workflow. Good. So now we only got the last module left. All right, so now let's take some time for rest and we will come back around 15 minutes. So 15 minutes now is like 15:05. So let's come back around x6:05. Okay, and then we will actually, hey, let me see, x6:05 should be only 10 minutes. Okay, so maybe x6:10. Let's come back around x6:10. So give you a bit more time. And then we'll go to the last section, which is talk about monitoring and some troubleshooting issues. Actually, it's a very quick module. So today probably we're gonna have a very early release. Okay, now module 6. Now we start to talk about something like monitoring troubleshooting. So I only got 3 lessons here, so probably it's quite a fast module, to be honest. All right, so let's talk about the HTTP response and the shard allocation issues first. So usually when we get back the responses from Elasticsearch, right, you will be looking at the JSON response. But at the same time, actually, Elastic returns you 2 information. JSON response is only one of them. The HTTP status is another one. All right. So it depends on how you get back this response code, right? For example, when we run HTTP, that kind of operations, right? We actually have a lot of HTTP connections and interactions with some REST servers. And when they return, usually there is a status code as well. So either 200, 201, 404, or 500, all right? So that's why one of the things that you probably need to do is to check the status code first, all right? Because the status codes actually indicate whether there's an error or not at the very beginning. And then to further look into the JSON response, you can actually get back the informations about what was actually happening at the back. So actually the JSON response is kind of like explaining what is really happening in general. So some of the common HTTP errors could be of some different status numbers. Now take example, if we're not just taking into consideration about the numbers, like for example, 200 or 500, the important point is what kind of errors we can get and what kind of operations we should apply when we get this kind of error. Now, one of the things is unable to connect. if the network, if it was a network issue, so one of the things is like I would say is like when you get something like unable to connect, the first thing you need to know is it a network issue or is it a hardware issue? Because when we talk about network, is it because your machine is already isolated or disconnected from internet? So that is one of the major reasons why you cannot connect to this cluster. All right. The second thing is maybe everything's fine. Now let's check your corresponding hardware. Is it something's wrong with the firewall at the very end so that you connect to the outside world? Maybe there's also a question mark there. So if everything's correct on the network and hardware level, now the next problem thing you need to test is if that Elasticsearch cluster endpoint is not available, what about other data nodes? So maybe server 1 is offline, but server 2 is still online. So that means the cluster is still running, just the endpoint that you used to connect with is not working. So if that's the case, you actually can shift the node address instead of like saying that is actually an error, right? And so usually the action is just check the statuses and check cluster health. So I would say check network status is important, but check cluster health. If you can't even connect to the cluster, how do you check? All right. So it's kind of like a bit silly, right? So what about number 2? Connection unexpectedly close. So this is talking about when you were talking with a node, but suddenly the node is not responding. All right. Probably something's wrong with the node. Kind of. All right. So maybe somebody suddenly shut down this node unexpectedly. So what you can do is usually again check the network statuses, of course. Is it your side having problem, or actually the other side, the cluster is having problem? Number 2, if we found that probably it's because the cluster has some glitches just now, maybe we should retry. But then here it says there's a risk of creating a duplicated data. The reason is because if you're running something like a post operation, right? We know that for post, we will create a document ID for you, and we don't check if there's any duplication of data at all. So that's why when you retry, there might be a risk that you are duplicating a data. Because just now, when you fail to get a response from the previous operation, maybe Elasticsearch cluster has already updated the data. Just it failed to send it back the response before it dies. So that's why there is a chance that you might be duplicating the data eventually. So on the other hand, on some other errors like 4xx is actually what we call client error. All right. So client error is a little bit tricky. So take example 4xx, it means that you have some bad responses here, right? For example, the syntax is not correct and so on. So that's why it might be what we call client error. So usually fix the JSON and you're always good, all right? So one of the things that you probably might have issues is like, because we're talking about JSONs, right? It should be using double quotes instead of single quotes. And if you were a JavaScript developer like I do, usually JavaScript, we don't care about double quotes or single quotes, etc. It's just a quote and it works. But in JavaScript, maybe in JSON, it doesn't. You have to use double quotes, all right? So that's why there might be an issue about this. Also, when your JSON is very huge, you might be missing a few phrases, right? Square brackets and so on. So all these might be issues as well. So try to use a parser. So any JSON parser on the web is useful. Go to that and check whether the syntax is correct or not. All right. What about 429? Now 429 is talking about something called Elasticsearch Super Busy. The reason is because now we are trying to pump data in, keep on pumping until the server side is actually kind of like out of resources to handle your request. And so it republish a 429 to you and telling you that, hey, stop. I'm kind of like at the edge. So don't push any data to me. If you keep on pushing, you might be losing data because it's just like a queue, right? So the queue is full. You keep on pumping it, so all will be gone. So all the additional data will be dropped because it cannot enter the task queue. So that's why 429 means that stop pumping data for the moment. So what you can do is to use something like a linear or backoff exponential backoff. So linear backup simply means if it was set to 10 seconds, then every 10 seconds try to republish the data again, right? Exponential is kind of like having a factor. So maybe the first one is wait for 10 seconds, the next is 20 seconds, and next is 40 seconds, and next is 80 seconds, etc. So it's kind of like a factorized backoff instead of a linear. So every 10 seconds, do a retry, that kind of thing. Now, 5xx is totally internal error. So that means something's wrong with the Elasticsearch side. So check the server logs in general. So I guess it's still connectable, but it's kind of like not working as usual. So you need to check what's happening. So maybe one of the reasons is this is full. So some of the nodes have a full disk, and so they cannot keep on driving data in, etc. All right, number two of these things. All right, so assume that we understood the HTTP status code and also some of the basic handlings like 429 or maybe 404, that kind of issues. Now the next situation is we might need to examine also the JSON response. So usually JSON response, there is a metadata at the very top. So telling you something like how many shots are involved. So this is usually the metadata that we kind of like ignored, but it gives you some very useful information as well. For example, number of shots involved in total means that how many shots are involved for this index operation. We assume that we need 2 shots. So probably one is a primary. The other one is a replica shot. And successful means how many actual shots have been indexed. In this case, also 2, which means all the primary and the replicas has been updated, all right, without any issues. So there are cases that sometimes there will be some failure operations, like maybe one success, one failure. So that might be one primary okay, but the replica is not okay. So it would try to indicate whether there's a failure message as well. So that's why in the failures clause, there will be some messages if provided. These are some of the examples of the response body. So if on the top left-hand side, we see that total is 2, successful 1, but no failure. This is actually okay because sometimes we do have only one primary shot available, but not any replicas. So that's why having successful 1 is actually acceptable. So on the other hand, the top right, you see that 2 failure means that both primary and replicas are failed, this is a bad issue, right? So something's wrong with the cluster environment, right? Because you cannot write data to it. So you need to check the server logs why. And the bottom one is telling you that if there's a failure and we kind of like can get back some informations, we will try to give you back that error message. All right. Now, understanding the search response body. On the other hand, for search, we also have this search body. And we also usually ignore this shot sector as well. So here we will see that most of the informations are quite the same. We have the total number of shots required and how many succeed to return a result, for example. And somehow we also have like some additional things like skipped. Now, skipped is a very ghost-like thing, all right? I would say it's a ghost-like thing because I never see it as a positive number, even till now. For so many years, I didn't see any non-zero values for skipped. So skipped by theory, it means that the number of shots that cleverly avoided on execution because they contain no data matching the query. So make it simple. It's kind of like caching. So inside a cache, we found that there should not be any data related to this search criteria. And so we simply skip those data shots. But to be honest, I really didn't see any positive numbers till now. I mean, after 5 years, I still usually see skipped to zero. So I don't know exactly how this thing works. All right. So anyway, just believe that in some days, if you have some criteria that match, you will see something like skip that is non-negative. But for me, I never saw it. So it's kind of like say it's a ghost field. All right. And so here is some of the response examples. So you can see that some of these are talking about partial results. So you can see we need total 5 shots to run the search, but only 3 of them return. So 2 shots are not available. So why? So a lot of reasons, right? So maybe some of the reasons is because the shots are not responding because of too many loading, or maybe the network for that particular node containing the shot is very overcrowded, or maybe, I don't know, it's not responding at all. All right. So there could be a case like that. And so that's why there's only 3 successful. And so this is what we call partial results. Now, the interesting debate is when you have a partial result, do you need to rerun the search? Okay, so my answer is if you are working for something like search engines, all right, like Amazon, that kind of e-commerce website, to be honest, having partial results is okay. All right, so take example, when you go to Amazon, you type in something and it returns you partial results. I'm happy because I'm the customer. And if I type in something and I see something coming out, I'm super happy because I can start picking the goods or products that I might buy. All right. On the other hand, if you are actually working for some government, working for banks, working for the medical industries, having partial data might not be acceptable. All right. Remember, if you're working for medical industries like doctors or pharmacies and so on, you should get back 100% of all the data so that you can do decision making. All right. Actually, because your decision might affect people's life. So that's why for this kind of situation, you need to rerun the search until you get back total and successful to exactly 5. All right. But if you're running some like e-commerce website, come on, getting some data back is okay, as long as the number of success is not too low. All right. If you say that only 1 shot return, you might need to rerun that as well. But if you have like over half of it, like 3, I'm fine with it. Just display all the results and do not disturb my business. All right. So that's why the debate is here. Depends on your business nature. You might need to rerun if you get a partial search result. So finding the health issues. So just now we have talked about the cluster health, right? And it gives you a color and some basic information like how many primary shots involved, how many total shots you should be phasing, blah, blah, blah. All right. So that's actually good, but we have some other things to deal with this API as well. Now, take example, when you really go into a bad situation, you have a red status. So what do you do? Usually, we will do a regular ping, like every 10 seconds, ping on it, and to see if there's any data coming back, all right, telling you that the status has kind of like improved from red to yellow or from red to green, all right? So every 10 seconds, you do a ping and run this cluster health, right? Yes, that's one way, but it also adds on some additional overheads to this cluster. All right. So instead, we can run a synchronized version of cluster health. So when we run cluster health, we set wait for status equals to a color. For example, when it reaches to yellow, it will come back to you. So it's kind of like blocking, a blocked function call. All right. It will only return when the status color change from red to something else. For example, in this case, to yellow. All right. So that will save us a lot of re-pinging operation. All right. So this is one of the ways to improve the situation, because if you keep on pinging, the server might be kind of like adding some overheads to handling this kind of ping at all right? Because it should be something like a red color, right? So somebody's kind of like fixing it. So we should not disturb the so-called therapy operation. Now, when we talk about the cluster health, we can drill to index level as well. So we want to know exactly, yes, I know it's a red color, but who's the culprit? Who is the one that create the red situation? So we can actually go to level equals to indices, and then the corresponding red indices will be displayed as well. So in this case, something called my index has a red status, all right? And you can see number of shots should be 5, but only 2 active primary shots are there. So 3 primary shots are missing. So probably something's wrong, all right? So maybe some of the data nodes are gone in which they contains all the primary shots and the corresponding replica shots, blah, blah, blah. So anyway, something's wrong. You need to know. And it tells you exactly which index is the one. You can also just take a look on a specific index health as well. So because inside your production level, you have so many data index, right? So what's the point to grab back indices all the indices have information. So instead, some very important indices, we want to know if they change to red status or not. For others, come on, it's okay to let them to be in red, right? So one of the clients in USA that I've approached earlier is like, oh, please wait, please wait. Okay, I'm back, right? So we're just now talking about is like sometimes we might want to know exactly which data index might be having a problem, but not the others, right? Now take example, maybe we've got something like transactions. We also got something like HR complaints, right? So these are the two sets of indices we have in our production environment. Probably transaction is more important than HR complaints, right? So HR complaints, just throw them away. If they got a red status, hey, come on, that's fine, all right? Less complaints, very happy. But when you have something like transaction, you want them to be intact for all the time. So you're checking the health statuses of transactions. So that's why you can use this syntax just to grab the information about TRX instead of something like HR complaints. Also, the previous thing that we've learned, like the level of indices can be applied to this syntax as well. Now, finally, we can also drill down to shots as well, so that we know that going to the shot level, we can also display all the corresponding shots that might have an issue, right? Instead of just the index level. Now, one of the final pieces of this lesson is talking about the allocation explained. Many ways, there's actually a lot of ways to troubleshoot, like, for example, why a particular shot is not working. For example, maybe hardware level or whatever. But the first thing is you might also run a cluster allocation explain API to know why that particular data shot is not working. All right. Now take example. If we run something like explain, it will give you a set of shots that is actually not working, and it tells you why. For example, this one is my index shot one. It was unassigned. It's also a primary shot. The reason is because cannot allocate because the allocation is not permitted to any of the nodes. Now, in engineering 2, there is an answer for this because you have set up the wrong allocation rule. So you cannot allocate the missing shot. That's one reason. Second reason is because some hardware issues. Maybe your mount point for the storing data is already full. We cannot write data to it anymore. So we can't allocate this primary shot anymore. All right. You can also give me some additional metadata so that we're displaying only the reason why this particular primary shot is not allocated. All right. So remember, if we just run this, it will just give you a bunch of problematic shots. If you give me the metadata, we'll just focus on this my index shot zero. And is it a primary shot? And why is not allocated? Blah, blah, blah. All right. So it might be much more handy if you know it. All right, quiz. Why should you bother to check the shots part of the response? Now, depends. If you're talking about the indexing, you will need to know exactly whether the primary shots are indexed correctly. Second thing is you might also need to know whether the replica shots are also indexed correctly. If not, you might need to take a look why. All right. On the search part is actually more important because when we search data, we usually will tell you how many number of shots are involved, but the actual number of shots returned is another issue. So it will tell you whether your search result now is a partial result or not. If it was a partial result, should you rerun the search? Like what we discussed just now, depends on your industry. If you're doing something like a website or maybe something like a search engine for some companies, it's okay to have partial data. But when you're talking about some important, not important, I would say it's like some industries that require full in-text data information, like for example, government, police, medical, you will need to rerun the search if you're having a partial result, right? So again, case by case. So probably in banks, you need to do that as well. Number two, having an unsigned primary shard means your cluster is not in good status. Yes, because you have a primary shard missing in general. So then that's why you should be in red color no matter what. Number three, skip the section indicates number of shards that fail to execute a search request. No. Okay, if you're talking about failures, you should have a fail clause describing this number. Skipped it is kind of like a ghost field, like I said. It's telling you that there is a bunch of shots that should be skipped in this search query because they never contain the required data for your search. All right. Even though for my 5 years working here, I never see this field to have a positive number. But theoretically, it is what I'm describing just now. All right, some shots that never have the results for your search, then they will be skipped. All right. All right. So now again, let's take some time to rest and like 15 minutes, 15. All right, not 50. That should be 45. Yeah, X650. Around this time, we'll come back and we'll talk about monitoring. All right. Okay, now back to the lesson. Now we talk about the second last lesson called monitoring. Because when we go into like productions, right, probably we cannot skip monitoring, right? So in general, monitoring the stack, right? To monitoring the stack, you can actually have a bunch of different ways. If you're coming from some very old versions of Elasticsearch, you can just click on the click on the button called monitoring and activate it. So that's the legacy way to make stack monitoring available. But in the current versions, when we talk about like monitoring the stack, we are actually trying to make use of metric beat and file beat. All right. So that's why in this lesson here, we'll be talking about the modern version that is using beats to collect the stack information, right? Instead of using the legacy way. So take example. Actually, not take example, right? We'll talk about that thing a little bit later. Important things is we also recommend you to have a dedicated cluster for storing the monitoring data. All right. Reasons are the following: because we want to reduce the load and storage of your targeted clusters. That's your monitoring cluster in general. That's actually one piece. The second piece is we want to keep access to the monitoring even during some unhealthy situations, right? The major reason is because even though your primary clusters, the target ones, are kind of like not functioning very well, but because we're using metric beats and file beats at the end, we might still be able to suck out all those information at real time to resolute what is really happening inside the target cluster. All right. However, if everything's on the production cluster, if it's not working properly, you probably also miss this opportunity to know what's really happening because everything's there. And now here, that piece is not accepting external connection. So you can never know what's really happening. But if you have a separate cluster somewhere, and we try to use file beats to get the data connected and so on, we can still get back all the monitoring data at the monitoring cluster. Even though this side is not accepting requests and so on, we can still get back at least the error logs, right? So that makes sense. The last piece is we want to support segregations of duties because different clusters, they probably have different security policies. And so we can actually apply those policies to different firewall rules, etc., and access rights. So now maybe administrators, they can always access this monitoring cluster. And for front-end users, they can't because simply there's no point for them, the front-end users, to know whether the cluster is healthy or not, right? So it's kind of like another set of rules that you can apply to, right? So it makes sense to the management in general. And so that's the reason why we recommend that you have a dedicated cluster, right? But of course, there's a cost behind this, right? We'll talk about the cost later on when we meet this slide. So the modern version of monitoring is to use the beats family, right? So how do we do so? So simply, we will need to deploy at least metric beat on every targeted machine that you want to monitor about. Now, take example, you might have different machines hosting Kibana, Elasticsearch, Node, etc. So all these machines, they need to have a metric beat installed, all right? So that's the minimum. And on the other hand, you can also monitor the corresponding file beats, the beats family if you want to, even though it's not kind of like not mandatory because for most cases, the beats are working fine and very efficient. Unless you find that the beats are not kind of like work as fast as it used to, then you might want to monitor whether something's wrong, right? So remember, all these information that was extracted from metric beat, we should send them to somewhere, right? So that's where we set it to be a dedicated monitoring cluster. So you can see there are two clusters in general. One is a production cluster, and on the right-hand side, it's actually the monitoring cluster. All right. So all the metric beat will try to get these information and push them to the monitoring cluster. And the reason is because we want to it's kind of like separate the loadings. And also, if something bad happens, the monitoring cluster is still online, right? And so that's the reason why you can see there's also an additional Kibana sticking to the monitoring cluster, so they can see the UI things, right? All right, so the steps. Now, deploying the metric beats to all the corresponding targets. Now, the first thing is in the Elasticsearch cluster, we need to activate the monitoring first, right? So we would just simply set a cluster setup core expect monitoring collection enable to true. So in your UI, you just need to click on the button to activate it. You don't even need to run this API, right? Then the next steps is, of course, every single target that you are expecting, you should install the metric beat. And also to start up the corresponding modules as well. So the simple example here is like this, right? Metric beat modules enable Elasticsearch expect. So now we will be enabling the expect module to collect the metrics on a Elasticsearch node, which is by default the local host one, all right? So this is the default settings. But in the production level, in which you might have multiple Elasticsearch nodes running on the same physical machine, then the corresponding setups might change because we're not listening to local hosts. Or at least maybe we're still listening to local hosts, but port numbers are different. So we need to provide these addresses, all right, IP addresses to the modules eventually. So here we just assume that you have a one node per machine, that kind of setup. So that's why it's okay to just directly enable the module and run it. And then, of course, the later one is to start your metric beat so that we start to collect the data. And you might ask us like, how frequent are we going to collect these data? It depends on the set of files, right? If the configuration for a particular metric set is set to like 10 seconds, then every 10 seconds it will start to grab something. But on the other hand, some metric sets that we configure could be like starting to collect data every 5 minutes instead. So that's why the configuration file determines how frequent these data are collected in general. And you can also disable the legacy monitoring feature by running another cluster setup. So you can see here, it is very similar. So this is the modern one I'm copying here, all right? The modern one is this setup, but the legacy one is something like this, okay? So the only difference is there is a Elasticsearch in between. So this is the legacy version, all right? It's kind of like okay to disable it if you're using the modern version. If not, you can actually have both of them activated. But it's kind of like strange because you're collecting the same data for 2 times, all right? So that's why be very careful when you're using the latest version, the modern version. Monitoring logs with file beats. Now, the second thing that we probably need to play with is getting the real physical log files from Elasticsearch. So how do we do that? So in the old days, we can actually use the legacy version, legacy monitoring to do so. But for the latest version, we should actually set up file beats to directly collect the data from those Elasticsearch nodes. All right, so what kind of logs should we actually monitor then? So in general, we have the audit logs. We have deprecation logs, GC logs, server logs, and also slow logs that we probably need to access, all right? And after knowing which kind of logs we should actually include, we will actually be setting up the configurations correctly. Now, for example, the whole deployment process is quite similar. You need to deploy the file bits on each of the target nodes as usual. You also need to activate a module. So this time the module is called Elasticsearch. That's it. Very simple. Not even have -expect. And then you can do an optional setup if you want. So this setup is talking about installing the dashboard information, that is the configurations in general, and also as well as setting the index patterns, that kind of thing. right? So it's again optional, but usually we will actually run the setup as well. So just now, actually, this step was missed, right? So dot metric B setup should also be run as well, because you also include the index patterns and the corresponding mappings for each of the files. I mean, each of the fields, not files, as well as the default dashboards. So this step is actually missed here. And finally, you can start your file bit as usual, and we'll start to grab the logs. Now, the discussion we've gone through earlier is we should have kind of like a dedicated cluster, because the dedicated cluster can also serve as monitoring multiple production clusters as well, like this, right? But to be honest, there is a cost behind this. The cost is you need to pay for a license. So the basic license that we grant to you once you download and install Elasticsearch is free to only monitor one single cluster. That is, you have one production cluster, for example, and your monitoring should be inside this production cluster, because you only monitor one cluster, including itself, right? So that's why if you want to do something like this, you need to pay for license, at least Go license, right? But I'm not sure here, because we have so many different students from different companies. Some of them, we know that you already have a license, so we can use this approach. But for some others, maybe you do not have. So probably you cannot run multiple cluster monitoring, all right? So that's why we recommend you to use this approach, but it's not free, all right? Just to let you know. So these are some of the cluster level dashboards that we have if you have installed the monitoring correctly, all right? And typically inside your labs later on, you'll be running these things. So I won't be showing you the UI for now, all right? And some of the information is usually, most of the information are related to the NUX level. So if you click on it, right, you can actually see some additional things like, for example, the memory, usually the heap, the I/O operations count, and also the CPU utilization and so on. So all these are very important, because if you see something that is extremely high or extremely low suddenly, something probably is happening inside your nodes. You can also read the indices information as well. So even though for most cases you probably don't need to see this, but at least we have the health colors, so that you know that this cluster is healthy or not. Is it a red color, or is it just a normal yellow, or just a green, right? So that's pretty much for the monitoring. So like what I said, is a very simple module in general. So it's just telling you how to prepare. Because when you go into production, right, you probably also need to not just monitor one single node, but a few nodes. All right. We told you that 3-node cluster is a must for production. Yes, we know that somebody's still using 2-node cluster for production, but anyway, the de facto standard should be 3, all right, or more than that. So that's why when your cluster size is growing bigger, you rather use some normal ways to collect the health matrices instead of running something like a ping operation. So I do know that some customers actually, they just run something like a ping operation and see if the cluster is still online or not. Yes, there's also one way, but how can you know if that online machine is actually still healthy? So you need some ways to kind of like collect these matrices, right? Yes, we've showed you that you can use APIs, right? Yes, that's true. But on the other hand, will that be too tedious? Because you're writing some scripts and pinging the cluster with the cluster health API, for example, every single 10 seconds, all right? That's okay. But then how can you kind of represent this information? How do you know something's wrong, all right? So you need to write a lot of other things behind the scenes. So that's not too efficient. And that's the reason why we introduce you the monitoring module, in which you can make use of it, provide some UI for you to at least quickly scan what's happening, who is the culprit, which node is having a red status, blah, blah, blah. So that's actually something useful. You can use metric to monitor all components of Elastic. Yes, that's true. All right. So the modern way to do monitoring is through deploying a metric beat. All right. So if we're talking about the latest one, we're actually using something called Fleet as well. All right. We're calling about Fleet and the agent beats. Okay. So the latest version that we have is something called Fleet and Agents. So agent is kind of like it's kind of like a general beat that can receive and connect to something called fleet control. So fleet is actually the UI. So fleet contains all the policies that you want to set up. For example, when you have a Windows workstation machine, you can define some policies like install a metric beat, install a file beat, and only look for application logs, but not Windows security logs, for example. So these are policies that you can set on Fleet. And then you install an agent beat at the target workstation. And so the workstation will connect to the Fleet UI, actually the backend servers, and then we'll download the policy and know, oh, so you need to have a metric beat and you need the file beat. Plus, your file beat just needs to grab application logs, but nothing else. So it knows how to do the deployment for you. So this is the most updated information about monitoring in general, right? But in this course, we actually will not talk about this because this is still a beta functionality. But this beta will become something like GA very soon in probably major version 8, I suppose, or maybe 8 point something. All right, so maybe 8.2, 8.3, it will be GA for sure because we're going to that direction, right? Number two, true or false? You can use metric to collect metrics as well as logs. Ha, no. So metric is for metrics. That's it. For logs, file beat. Okay. So that's why it's not true. You cannot. I mean, every beat has its own mission. It won't be kind of like stepping into another beat's so-called grounds to snatch the work, right? So for reading log files, we will be using file beats no matter what, right? Number three, what are benefits of a dedicated cluster for monitoring? Okay, so if you forgot, go back to that slide, the three reasons, right? Like for example, segregation based on policies of the security, removing workload for the primary cluster because we don't want them to be disturbed, and also store some monitoring data. All right. Usually, monitoring data for most cases it should be fine because we don't really have much issues on that. So storing these things are kind of like useless, right? Wasting bandwidth as well. And finally, the last thing is if something really bad happens on the primary or the production server, we still have a way to look for these monitoring issues based on a monitoring cluster. All right. So that's the reason why we separate them. But like I said, there's a cost. You need to pay for a license to make sure that you can have multi-cluster monitoring capability. All right. So it's not free. Yeah, it's kind of like tricky because we usually hide this information from the course, right? But I will let you know because have to be honest anyway, right? If you find that, hey, it doesn't work, right? The reason is because you cannot do so unless you have a license. All right, so now the last lesson. So let's take like 15 minutes again, and then we'll come back for the last lesson. And we probably will have an early release. So 15 minutes. Now it's 10, 15, 25. Okay, so let's come back around 25. And probably we can end the class within 30 minutes from that. Okay, let's see you. Okay, so the last lesson, right? So earlier, the first two lessons, we've talked about something like some of the UI things on monitoring and also some basic APIs for getting the health cluster, the clusters health, not health cluster. All right. So now there is actually one more lesson talking about the APIs. So in general, if we are not supposed to use APIs, sorry, I mean, not supposed to use UIs because we might be administrators. We don't even have a Unix-based access, right? So in some companies, yes, there is a lot of people that actually works in the terminals. They do not have something like UI, even though it's kind of like getting weird, but there is people like that working in banks, right? I actually has a job that is always working on terminals, but not UIs. So that's why we also tell you how to get back the so-called diagnostics through the API way. Because if you're in a terminal, you will be using APIs only. So the first API that we want to talk about is the CAT APIs. So instead of going into the slides, let's have a demonstration. All right. So this is the Dev console. All right, make it bigger. Now, in general, when we're talking about the CAT APIs, they're super useful for creating some diagnostics for us in a tabular format, something like a table instead of like normal JSONs. All right. So take example, we do a CAT. Usually there are a bunch of possible options. You can see so many CAT options, right? So if you have no idea what I can do with the CAT API, just get CAT. And you can see a pretty CAT here plus a bunch of possible API calls. Now, usually we start with indices. You want to know exactly what kind of data index do I have inside my cluster environment. And then you will see a bunch of things like this, right? So this is the tabular form, even though it's not very nicely packaged. So let's resize it a little bit. So now you see that it's kind of like having the color of the index, the status, and also the index name, etc. Right? And some IDs as well. And so there are some interesting things like 1011, what is that? And also some numbers like this, what is that? Also some k bytes. I guess this is probably talking about the size of the total index, etc. So we're guessing some of these things, right? So in general, when we run the CAT APIs, we should have V here as verbals. And if we run in verbals and make it smaller, you will see that now the first line is talking about the header. So just now we saw some 1 and 0s, right? It was talking about the primary shots. 1 primary shot, 0 replicas. And docs count is the next one. So that's why you guess this is kind of like number of documents. Deleted documents, here is at 0 or 4 or 1 or something, right? Also, what about the size? So there are two sizes. One is talking about the primary shot size. The other one is talking about the primary plus replica size. All right. So in here, because I'm having a 1-node cluster, so that's why everything's the same. But if you have a 2-node cluster, you will be creating replicas, right? So the size should be doubled. So now we have so many columns here, right? But to be honest, most of the data is not so relevant to me. I just need, for example, the index name, right? I just need this column and probably maybe number of documents, docs.count. So what you can do is to pick by using the H parameter. For example, index docs.count. And run again now, you just reduce the table into 2 columns only, index and docs of count, right? And sometimes you might also want to sort this operation as well, because now you can see they are kind of like displayed in some random pattern, right? So S means sort. Sort by what? Index, ascending order or descending order, and run again. Now you can see they are all sorted in a particular way. If you want, you can have descending order as well. All right. Now, final piece is even though I've kind of like sort this information, but maybe the ones that I want to grab out is actually related to blocks only. So what should I do? So you can actually add index equals to blocks. And so only the blocks will come out. You can always use a pattern as well. For example, you got logs 1, 2, 3, right? You would just say log star, and then you get back all the logs coming back as well. So you can also have a star at the beginning as well. So you also get back the blocks. So that's how we kind of like customize the CAT APIs. So CAT APIs contains a lot of other useful diagnostics for us. For example, CAT nodes. And so you see that I'm only got a one node cluster, but a bunch of numbers. Again, the first time you have no idea what this is, always use a V here. So now you know this is the IP address, number of heap usage, how many CPU I have, loadings per 1 minute, 5 minutes, and 15 minutes. The roles, for example, is a data node, is an ingest node. L is I forgot what's L though. M is a machine learning. Sorry, L is machine learning. M is master eligible. R is remote cluster client. T is transform. Yeah, so L is machine learning. So it's a little bit confusing here. And you also have the name named as node 1. Also, it's a star here, which means that this node 1 is the master, right? So that makes sense because the differences between running the normal APIs versus the CAT is, if we run a CAT nodes like this, you'll see that we have returned a very huge JSON. And this JSON is comprising like 900 rows of data, all right? And if you look into it, all right, you can see that it's also called node 1. Where is node 1? Let me just find the name. Node 1. You can see that there is a subset of this huge JSON describing the name of this node as node 1. All right. And also the roles now will be all in full description. For example, it's not DLMRT, something like that. Instead, it's data ingest master, ML, blah, 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 etc. Right? And some other additional information that you probably might not even touch. For example, the HTTP controls, the protocols, is actually using netty. So to be honest, we don't really need to know this depth. We just need to know, do we have HTTP? That's it, right? And some other attributes, like, for example, there's a transform node to true, expect install set to true, blah, 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 etc. So all these things are, and even the JVM related parameters, they are all here. For example, G1, GC, blah, 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 XMS, XMX should be somewhere. XSS, XMX, that's just 1 gig only. So you can see all these things are all included in the original API for nodes. But to be honest, most of these are not too useful. Instead, returning just this minimal information is good enough to understand what is, how many nodes are involved, who is the master, and what roles they are with the basic IP address. All right, so that's why if you're integrating this information with some other systems, running the normal API is good because they provide structured JSON data. But if it's for humans to read, using CAT APIs will be better because it's tabular and we all understand what this is, right? Much easier instead of traversing that big JSON. So that's the reason why we have 2 APIs in general. The normal APIs plus the CAT version. So like what we said, usually it's good to specify the columns because when we want to display only certain columns of data, we should actually use the H parameter to select those columns for displays. Pending task. So actually in Elasticsearch, we have 2 task APIs. One of them is called pending task, which is talking about like you are throwing some job to Elasticsearch, but they are not picked up yet. Right, so that's what we call pending task. In general, pending task is kind of like a very rare scenario because we should be able to grab all the tasks and make it work at the very beginning. All right, And once we pick up this task, we throw this task to another queue called task queue. So that's why we have another API to grab what is really happening inside the Elasticsearch now by running get task. So you can see here, every task is under a particular node, right? So you can see the biggest or the parent values is actually talking about describing which node it contains this task, right? And then it starts to talk about is like the task ID. So the task ID for this particular task is this value, right? So you can see that there's a number as well. So 37 something. So this is equivalent to something like the process ID. So later on, if you want to cancel this job, you need to have this ID as well in general, right? So that's the idea. So everything that is actually running at the moment, they should have a task record. And so that's why you can run a task to see them. In which log file I get info who accessed via API. So we do not have this thing. If you need to get this, I think you need to either write your own programs to have some audit log, that kind of information. So we do not have this information, all right? So we're not like HTTP servers, but we do not have that kind of access right. So if you want to use them to apply some like audit log or audit trails, that kind of thing, you need to write it yourself in your programs, all right? And we assume that you're not exposing Elasticsearch directly to the outside world. If so, then we will never be able to track because Kibana itself doesn't have tracking as well, all right? So let me see, do we have? Okay, so one more thing to correct, all right? If you have XPack monitoring, there should be one feature that is talking about audit trails, all right? So if you have it, you can actually, you have a license, you can activate the audit trail, then you can actually track something similar to this, who accessed the API, okay? But for normal situation, if you do not have a license and you don't have the XPack running, etc., you will need to write your own programs, all right? So I suppose that's clear, right? So either you pay and you get this function or you write yourself, right? So usually my clients will be writing their own because they're not buying license at all, right? But if they already have the license, of course, just kickstart them. So let me just do a quick search on the audit trail thing. Elastic XPack audit trail or audit track, I forgot. They have a name there. And also something like this. So there are two links in general. So this link is the blog version talking about how to enable the audit trail. And this one is actually talking about the APIs. Okay. Now, additional information. When we activate the audit trail, right? There are totally two options for the moment. You can either throw every audit information on the console log. So that means inside your normal Elasticsearch logs, you will be able to see these things. Or maybe we throw them into a normal data index. So we just treat all the audit logs like a normal data index and throw it there. All right, so depends. I would say for most cases, you probably might want to make them into normal data index so they can search them. You can draw dashboards and visualizations on this data set. But on the other hand, if you are actually forwarding all these audit trails to somewhere else, like another system to analyze, then you probably want them to be inside the normal system logs, all right? So just let you know, they're totally generally two outputs, all right? But you need to pick which one do you want. Should you throw them to the console logs or should you throw them to a normal data index, all right? So that should work. But remember, you need a license for that. So one of the other things that you might want to notify, like for example, something similar to what Suta was asking just now is, can I actually add some additional information for each of the API calls? Well, if you're using the curl command, you can modify a header So you can add an HTTP header called XOPIC ID, and you kind of like provide some metadata that can describe this particular user. Then when we run the task APIs and so on, we'll see that it was actually initiated by some users from some machines. All right. So this one depends, right? I would say if you're using curl or using some programs you're writing, you can always modify it by adding the HTTP header, right? But on the other hand, if you're just using, you're exposing Kibana to your users and let them play with it, of course, the XOPIC ID header will not be included, all right? Because on the UI, there's no way to provide this additional header. So that's why it depends on how you expose the system. So we assume that you're not directly exposing, you're using some programs, good. Then you can always add back the missing XOPIC ID when necessary. And also, it should be a dynamic value because different users probably should have different IDs or some other metadata that describes who he or she is. All right. So you can also use this version to do some like audit trails if you want. All right. Some other things about the API levels is the thread pools. Now, Elasticsearch is kind of like a multi-thread server engine. So there are a lot of different worker pools in general. So each of these worker pools, you might want to get some diagnostics based on that. For example, get nodes thread pool, or maybe the stats version of the thread pool. Now, usually stats is giving you much more statistical information instead of the overall thing. So you can see on the left-hand side, we're just talking about the right pool, describing that it's a fixed pool, which means that it will not expand no matter what in the size and capability. And the size is only 4. However, the queue size is maximum to 200. So you can queue to 200 write requests. But currently, we only have a size of 4. That is 4 entries inside this 200 queue. On the other hand, if we want to know more statistics, like for example, how many threads are allocated for this thread pool, in this case, we found that there are 8 threads for this pool, and how many was actually queued, active, reject, and the largest size for the pool itself till now is only 8, for example, and how many completed, that means how many has been processed. So these are stats. If you want them, you can actually run the stats API to get back this further information. In general, when you run like a cat API like thread pool v, you will see that every single node has a bunch of different worker thread pools. And so these are some of the statistics that we can actually look into it. All right. Next piece is called hot threads. Now, hot threads is again a good to know thing only because it doesn't really tell you where is the culprit. So hot threads is talking about like inside this node, we've got so many threads running, right? But which thread is using a lot of resources? So good to know because the reason is they didn't tell you the task ID. So even though you know something is working, chewing up the resources, but I can do nothing because I do not have the process ID. I cannot cancel the task. So that's why good to know. And the syntax is you can run get nodes hot threads, which is getting all the hottest threads from all the nodes inside this cluster. Or you can directly say, hey, I want to know the hot threads for node 1 only. All right. And in this example, you can see that the hot thread is actually related to something called snapshot. And snapshot is a backup. So that's why it will be using quite some resources, which is normal. All right. And I suppose this is also one of the reasons why we do not give you the process ID. Because if you see that, oh, this is chewing up a lot of resources, but you do not know what it is, and let's just cancel it, oh my God, your snapshot will be gone. All right. I mean, it's not gone, but it's not performed correctly. So you do not have a correct backup. All right. So that's probably an issue. Another thing that we can do applied on the cluster is something called the index and search slow long, right? So they're typically the same thing, but focusing on different use cases. We know that we will be indexing data into Elasticsearch as well as searching data from it. So that's why for different processes, we provide you some thresholds. So these thresholds help us to identify what kind of operation is so-called slow. Now take example, the indexing slow log means that if indexing a document takes more than 10 seconds, this is a warning, all right? And if it's less than 5 seconds, well, maybe locked down as information. And when we say something like trace, probably 0 seconds because we want to trace every single index operation, right? And so pretty similar to Log4j, we actually can set the level of trace as well. So in here, we'll be setting the level to trace, which means everything. In production, we probably will set this to something higher, like at least info level, I suppose, right? And maybe even like warning levels, because info level is only 5 seconds, still acceptable. But something more than 10 seconds is probably problematic, right? And the final thing, source 1000 means inside the log that I'm going to lock down this slow operation, I only include the first 1000 characters, all right? This is again makes sense because if it is slow based on the size of the document, which is maybe some 10 million characters, for example, of course it's slow, all right? And then if we want to lock down the culprit document that makes this index slow, why should we actually include the whole million characters there? So instead, just give me an idea, the first 1000 characters of this message instead of the actual one. If not, you're actually also increasing the log file size as well, right? So eventually you're kind of like creating some additional unnecessary problems, right? So that's why source can be set to a maximum of how many characters to include in the final log. For search, it's pretty much the same thing, but the differences is we probably will have two thresholds because we have two phases, query and fetch phase. And so that's why you can see we have two different thresholds for these kind of operations. And the same, and for the others, it's pretty much the same thing. So we can also set the source, the level, etc. All right, nothing is different. One of the final pieces that we want to introduce you to know how sucks a search can be is by using a profile API. So profile API works like this. You run your normal search query as usual, but you add the profile to true. And so a not very human readable JSON explanation will come out, telling you where is the bottleneck, why is it slow, etc. So in general, we also provide you the same search profiler, but in a UI way, all right? So now you get back something like a tabular form instead of like a big JSON with some not very human readable explanations. So this profiler also provides support for aggregations as well. Final piece, that is the last slide for the whole class, is the circuit breakers. Now, circuit breaker is a concept that you need to know because in the very early versions, we do not have circuit breakers. I think it's starting from version 5, we start to have circuit breakers. And circuit breaker works like this. If you're trying to do something that is very memory intensive, take example, we will actually kick you out, stop you from doing it. So one of the things that one of the students asked at the very first day, I think, is talking about the 10,000 document limitation, right? So the limitation is because we do not want to do deep paginations in which we're taking a lot of memory resources just to filter out and find the 10 results for that very far away page, right? So that's why we kick you out if you are having more than 10,000 documents limitation, that kind of scenario. So this is how the circuit breaker comes into action, because circuit breakers are installed at different stages, different operations. When the parent or its subsequent child, if they found that there is a kind of like illegal or illegal usage of memory, that kind of thing, we will actually kick you out. All right. So either it is triggered in the child level or the parent level, we will still kick you out. All right. So it actually saves us because if you go into a situation of out of memory, is usually an error, not an exception, which means that if you are a Java developer, you know exceptions, we can recover from it. But if it was error, usually we cannot recover. So the only way to kind of like save your notes is to restart the node. So what's the problem of restarting a node then? So we always do that, right? The issue is if you go into out of memory exception, that means some things is working at the same time. So maybe inside the index buffer, there are some in buffer information that is not written to disk yet, and you need to force restart the node. So all the in-memory things gone. So you're missing documents, all right? Also, at the same time, you might be indexing something which is using memory, and you do a hard reset. So for that index operation, probably some things disrupt, all right? So that's the reason why going into out of memory is not something good. And we try our best to safeguard you by kicking you out at the very beginning, all right? But remember, one disclaimer is this is not a 100% guarantee operation. So we try our best to kick you out beforehand, but sometimes it doesn't work, right? So because maybe of bugs or maybe we didn't develop the things correctly, so be very careful. So it's not always kind of like a bulletproof protection. Good, we finally gone through all the contents, right? Now, the last information I probably want to sum up for this class is this discuss forum, right? Now, remember, after today, when the course is kind of like over, if you still have questions, try to ask your questions in the discuss forum here, all right? So all the supports and the engineers in Elastic, the company, they will monitor the discussion boards and they will try to give you answers when necessary, all right? So again, this is not a free consultancy, so you cannot ask them to provide you full scripts, all right? For example, I do not know how to write this. Can you provide me the script, the answer? No, they won't do that. But they will give you ideas. For example, the correct documentations, some blocks, some examples. They will guide you through that, all right? So it's not a free consultancy, but they will provide help for you to make sure that your script can be run, for example. So that's actually a good thing because even though it's not free consultancy, but at least they give you some ideas how to solve it, all right? And of course, if you have budgets and money, yes, you can call us. We can help you, right? We are kind of like servicing departments. We can help you on doing some of the jobs as well. All right, so for the trainings, just to let you know, we do have a certification exam. If you are kind of like confident, you want to take the exam, yes, go for it, all right? But the thing is, you should actually finish Engineering 1 and Engineering 2 course beforehand because some of the advanced topics is actually not that simple. So for this course, maybe most of things are very easy to you, but for Engineering 2, we're talking about some solutions and some advanced use case, which might take up some time to pick up. For example, writing scripts, all right? And also using something like lifecycle management policies, right? So all these things you would need some time to learn. And probably the best way is either through the official blogs, documentations, or actually attend the class Engineering 2. So before that, I don't suggest you to take the exam, all right? If not, you're probably gonna fail. So that's not a good idea, all right? So that's the Engineering 2 course agenda, skip it. Okay, final piece, the services company, so, or the department. So we're actually, I mean, the training is also under services in some general ideas. And if you find us as consultants, we will actually provide services on these things. And just one important fact that I need to clarify is we're not selling ourselves to you. So that means that we won't be with you for a very long time. Like maybe we'll be here for every week, I mean 1 week, like every 3 months, that kind of thing. And if you want people to be there like whole year, we will actually work with the partners, and the local partners will actually have people to work with you instead. And we're kind of like project managers to manage these things, to work out, and also to look after you, of course, If you find that the partners are not working well, you want to complain, yes, find us. We'll do something and we'll make you happy, blah, 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 etc. So that will be the idea, right? So depends, right? Anyway, if you got any real technical issues that you want to solve, you can always find us or find the salesperson in your country. And I think it's Arif, right? So you can find Arif, which is actually the sales manager for Indonesia in general. So he will help you out. He will know who can help, etc. Or maybe sometimes kind of like free as well. But it depends on what you're asking for. So thanks for being here. And the last point is go back to the learning portal to download this PDF, right? So it's important because if you don't download it, after 1 month, we will destroy that, all right? So download the files before we do so. And the last piece is we do have the quiz answers at the back. For example, sometimes I will skip some of the quiz questions, right? So they are actually at the very end of this presentation, this PDF here. So nothing is lost, right? Okay, so now the last thing, you still have 1 more day to run this environment. So tomorrow, this time, this environment will be gone, all right? So that means you still have 1 full day to play around with the labs or to do something disastrous, you can do it, all right? It's fully up to you now. And so I will stop here. And if you need any help, just drop a message here or maybe ask the salesperson in your country so you can actually get some help from us. All right? So thank you.